Okay. So you guys want to learn about kinetics, huh? That's what I hear. So, has anybody had a course in kinetics at all? Anybody had anything at all? College level, grad school? Tell me what you guys have had. How much kinetics are in there? It's mostly mechanism, mostly electron pushing. Yeah. Yeah. Is Kyle coming in? Okay. That's fine. I'm sorry it's so last minute to let you guys know about this. So,
So can you just, will the class be taught every week this
I haven't figured it out, but yeah, that's kind of the plan, at least that often.
Because we can try to reserve like 301A.
Yeah, this isn't so bad, but let's see how it goes. Yeah, at least this often, if not more often. We'll see how it goes and how much demand there is. So, well, what I thought, we're going to talk about kinetics, and we thought we'd talk about enzyme kinetics in particular, although a number of different topics will come up. So let's just start out. Okay. See how this goes. And so the first thing that I typically do, and I just kind of jotted down a few notes. Mostly I'm doing this off the top of my head, but there are a couple books that I like. One is this one, which is Alan First's Enzyme Structure and Mechanism. This is an old edition of it, but I know where everything is, so I like it. I can find stuff in it, and it's not an easy book to use, in my opinion. You have to come to it with some knowledge. It's not just it's not 101. It's like 201. And then there's this book, which is Jenks's Catalysis and Chemistry and Enzymology, and this is like 501, okay, level. But it's got some things in it that are that were very helpful to me at various points. So my enzymology and stuff is almost entirely self-taught. I don't know if that's a good thing or a bad thing, but I had to figure a lot of stuff out on my own. So I'll try to show you not only different mechanisms and things, but how to arrive at them. So when you think about an enzyme, the first thing you do is write down write down some sort of mechanism. And so you have E, which will represent our enzyme. I'm keeping this general because there's not RNA people in here. Otherwise, I'd put down R for ribozyme, which I'm tempted to do, but I won't. Okay, and it binds some substrate, right? And they come together. And what do they form? Right. Yes. Okay, and there's a forward and a reverse rate constant for that. And that's ES. It also has a special name, if anybody knows. It's called a something complex.
Michaelis complex?
Yeah, it's called a Michaelis complex. And now I just have to remember how to spell Michaelis. AE, thank you. That's what I was going to do. And then this thing can go on. And today we're going to keep it as simple as possible, but then we'll build up on the complexity of this. So if you look at this and think it's oversimplified, you're right. Because it doesn't go from ES to E plus P. It's got to go to EP to E plus P. But we're going to ignore all that for now, like most textbooks do. And so you tend to write down rate constants over all of these arrows, right? And so my favorite nomenclature, although not everybody's, is the first step is K1 to go forward, and to go backwards is K minus 1. But you'll see different things in different books. So, and then to go and form products, we can call this guy K2. And notice also, so I'm recording all this, so a lot of this will be in my words. Hopefully it'll record okay, and I'm not going to write everything down. But you'll notice that I use little script K's for rate constants, and I'll use big K's for equilibrium constants. And that's pretty conventional. Sometimes you'll see people use K1 for this guy here, and they might use K2 for that one, and they might use K3 for that. Okay, but I like I think it's caught on to do it more the way that I'm doing it. All right. So everything you do is rooted in something really simple conceptually. Like that's really easy to look at and think about. And one of the things with this is that you can take this and write down some rate laws and rate equations. And there's a couple of different ways to handle this that you can choose as an experimentalist on what to do. You can choose to have enzyme in excess, or you can choose to have the substrate in excess. And conventionally, it's the substrate that's in excess. And I'll start with that, excess substrate, or so-called steady-state kinetics. And I think the reason that that's probably conventional is historical and biological. Historically, it was hard to make lots of enzyme. It was isolated. Like urease, I think, was one of the first ones that was studied. It was certainly the first crystal structure in really small amounts. People just couldn't get lots of it. And I think biologically, enzymes are usually very limiting, and they turn over the substrate many, many times. Now, the RNA aficionados know that RNA doesn't always behave that way, and it's different, and it's often single turnover, and we'll come back to that. So we'll start with excess enzyme. And I'll use a little subscript 0 to denote the initial amounts. And it's flickering, isn't it? I don't know what it was doing that last night when I was playing with it. It must be coming from the iPad, maybe where I put my hand. That's 0. And I'm lazy, and I don't always put concentration symbols in. And I messed that up, didn't I? Let's go back. I love this. I can just erase it. Oh, wait, I have a little eraser somewhere. This thing? Look at that. Lovely. Okay, so the substrate's in excess. And this will faithfully record all of my mistakes, at least verbally, but maybe not written. Okay, and actually you don't need to make any assumptions. It just makes the math easier. You could write this down without any assumptions. And so what we want to do is to be able to plot the data, and we want to be able to pull out these rate constants, right? So that's kind of the goal. The goal is to get your Ks. All right, so let me go on to another page. I'll try to keep the amount of stuff on any given page relatively small. So how do you do this? Well, you have to write down some rate laws. And so the first thing that we're going to do, and I don't know how to have both of these up here at the same time, is write down the initial rate, and that's the rate at which you form product. Okay, and so we can write that down as V naught is a velocity, and so it's got to have units of like driving your car, miles per hour or something per time, and so it's going to be the change in the concentration of the product with time, dp dt, like that. And so so we can actually go ahead and write down what that's equal to. So if I go back, dp dt, if you look at our mechanism here, what is dp dt going to be equal to? What's the rate law for that? Well, there's only one way to form it, right? Through K2. So it's K2 times what? Anybody? How do you write down? This is freshman chemistry. And you guys TA this. Yes. Go ahead, Laura. Say it again.
Yes.
Right. K2 times the S, right? Recall. If you have A goes to B, some rate constant K1 dA dt is equal to, or minus dA dt. Yeah, let me back up for 1 second here. Let's write this in a slightly better way. The product formation here, which is dB dt, is equal to K1 times A. Does that ring a bell?
Mm-hmm.
First order rate equation. And that's also equal to minus dA dt. And like I said, I don't always put the concentration brackets around that. So, you know, this is a good thing to do when you're rusty or you're stuck, is to go back, right? Think about really simple situations. So with that said, everybody, I'm sure that rings a bell with everybody. So let's go back to the previous page, and if we want to know dP dt, it's just going to equal to K2 times ES, right? Because that's the only way that flows into it. There's nothing flowing out and there's nothing else flowing in. So it's going to be equal to K2 times ES. Like that. So, but we don't know what the concentration of ES is. And so what's typically done, if we go back to this, is to use a steady state assumption, if you guys remember that, okay? And focus on, instead of dP dt, let's look at dES dt. Okay, so let's go forward. So dES dt. And then if we go back, so it's formed only one way. There's only one thing feeding into it, which is K1 times ES, right? Okay, so we can go times E times S. But it's got a couple ways to break down, right? So one is ES times K minus 1, the other is ES times K2, right? So so if you look at it, again, focus on ES right here, you can see that there's one way flowing into it, and so we've already accounted for that, and then there's two ways flowing out. One is going this way, and one is going that way. All right? So let's write those down. And those are loss. Those are not gaining. It's going away. So one is K minus 1 times ES, and the other is, I think that there is a way where I can do, let me see if I can do this. So minus the other one, which was K2 times ES. All right, so just go back and look at it. You can see both of those. And so now we can factor out the ES. And also that change of ES with time, what's that equal to? 0. It's equal to 0, and that's the steady state assumption. We don't have to make this for single turnover kinetics, but it's not trivial to see that, and we'll come back to that later. Okay, it's equal to 0, and so we can factor out ES, rearrange, and you can come up with an equation. You can come up with you can fill this in later, or you can do it in your head, and you can see that E times S over ES is equal to, you could factor that out, pull that over, K minus 1 plus K2 over K1. Okay, and that's called the Km. The Michaelis constant, as opposed to the Michaelis complex. Okay, so that's the Michaelis constant. You guys have any questions? Did I lose anybody yet? Okay. All right. So let's go back. So the goal here was to get rid of ES because we don't know ES. Now we could solve for ES here and get it in terms of E and S, right? And but we don't know E either. So one thing that's often done at this point is to look at this and to think about mass conservation. So let me see if I can shrink all this down again. That worked really well. Part of this is me learning how to do everything. I'm going to try that one more time. Oops.
Bless you.
Bless you. That's not quite working. There we go. Oh, this is fun. Okay, and so we can write down statements that have to do with mass conservation. And so one is that E0 can only be in two places. Total enzyme. It can be E and ES, right? So if you go back and look at this, okay, it can be free E right there, or here, same thing, or it can be ES. Okay, so oops, come back. There we go. Okay, so let's go and write that down. And we can write down a similar statement. S can be in only two places. So, it's one thing to watch somebody like me go through and solve this. It's another thing altogether to sit at your desk and try to solve it by yourself. And so there's generally helpful to have strategies rather than just watch me do it. So I would say the strategy here is we go back one slide, is we need to get rid of ES. Because we don't know it. And we also need to get rid of E, because that's free E, right? It's not initial. We don't know how much is free. We need to get rid of both of those things. And so in order to do that, I'm going to use this equation right here, because I do know the total amount of enzyme. But I don't know E and I don't know ES. And so, yeah. And what I want to do is first get rid of E. And then substitute in ES. Okay, if that sounds like a good strategy. So if I can get E in terms of ES, this has no. Does this guy have a? Is that what this thing is? No, I didn't want that. I thought there was a laser pointer on this. But I'm thinking of a different one that I was using. There is no laser pointer on this. Anyhow, so I want to do that, and so the first thing I'm going to do is try to get rid of E out of this equation here, and in order to do that, I'm going to go up here and solve for E. Okay, so let's go ahead and do that. So. See if I can try this one more time. I think I'm getting the hang of this. Doesn't seem that way, but I think I am. So let's solve for E out of this equation there. E is equal to, make this smaller first, or bigger on my screen. E is equal to Km times ES over S. And that just comes out of that equation right there. And so now what I'm going to do is I'm going to substitute this into here. Right, so that'll give me that E0 is equal to Km ES over S plus ES. And now I can factor out the ES. And now I know what ES is. And that's really critical. And so I'm just going to rearrange this and solve for ES. Maybe I'm pushing too hard. And now that I know ES, what can I do with that? Well, I can substitute it back into this equation right here. So, so I'll have V0 equals K2 times ES, or equal to this. And I know all these guys. Like that. And I actually like to look at the equations this way, but that's not the way you're going to conventionally see them. You'd probably, most people would multiply this through by S. So if I take this guy, I don't know if it'll copy it for me too, it might. You'll see me get better as the time goes by. I hope so. Hopefully I won't get worse. Lovely. So, well, we lost the last part of the E. We can fix that. So one thing you can do is always multiply by the number 1, of course. And so if you don't like that Km over S in the denominator, and that's often what's done, would then be, once you do that, you just end up with K2 E0 S over Km plus S. And now S is free S, but if you go back to the mass conservation, remember that we said all the way back here that S0 is in huge excess over E. So if that's true, then this guy is approximately equal to what? Right there.
Which one?
S0, right here where I put the question mark. S0 equals S plus ES. It's approximately equal to S, right? Okay, because there's not very much E, so you can't get very much ES. So it's approximately equal to S. So S is approximately equal to S naught. So I can put that in here. Because I definitely know the total substrate. Hopefully I do, because I set up the experiment. Like that. And that might look familiar to some of you. Erica, does that look familiar?
Mm-hmm.
Some people simplify this down even further. And so, but there's a couple things that I'll say about this before I do that. Well, yeah. Let me just write these things out different ways, okay? So one way that I like to think about this is to look at it like that. All right, and because if you look at this piece, you can see that has certain limits, right? So when S naught is really bigger than Km, the whole thing's going to go to 1. And that's the biggest the rate can ever be, right? And so this has a limit of 1. And that's basically, if you were to go back a little bit, you should be able to figure out that that's actually equal to the fraction of ES. Okay, I didn't try to do that, but it should be equal to that. We can try to do that in a second. And so then this is the fastest the rate can ever be right here, because when this is 1, so this part is called Vmax, because it's the fastest the rate could ever be. And so people will say that this is equal to that V naught is then equal to Vmax times S naught over Km plus S naught. Okay. Let me just see something for a second. Yeah, you definitely could show that that's true, that that's the fraction of ES here. So this guy is fraction of ES, which is equal to ES over free E plus ES, right? And that's equal to, so I don't know if you know how to show that those two are equal to one another, but one way to do it is just to divide top and bottom by E. Like that. And then if you go back, you can see that ES over E right here is equal to S over Km. And so that, therefore, that this whole thing is equal to S over Km over 1 plus S over Km, which is equal to that if you multiply through by Km. So this whole thing here is equivalent to the fraction of ES. The fraction of enzyme that's saturated with substrate, and the fastest it can go is when it's completely saturated. So anyhow, that's just kind of an aside, but this is a classic equation right here. So let's see, we have that. Let's do some really just traditional things with that rate equation. This stuff that I did here, don't worry about it too much, but maybe if you go back and you play this over, some of it's going to go fast and some of it's going to go slow. That's why I'm recording it. So if you're interested, you can go back and you can play it again. Hopefully that will work, and the file won't be too huge. I think I can put these on YouTube. I made my first YouTube video the other day. I made 2 of them. I got an email that said, "Congratulations, you've made your first YouTube video." All right. So let's take this. Let me see. I guess I can copy this, can't I? Save myself from having to write it. All right. That's cool. So let's plot. That's one thing people do. So one obvious thing that's done is to plot the initial rate versus the concentration at S0. And so you may recognize this equation. Does anyone know what kind of an equation that is? It's a square hyperbola. Okay. So you can, you need to, if your math is rusty on doing this stuff, you need to brush up on that. And so, I always take limits, and if you want, I can write the limits out, or I can just do them out loud. But maybe I'll write them out. So, so one limit is when S0 is small compared to Km. Oh, and the other thing to note is that, you can only add two numbers together if they have the same units, right? And so S0 and Km have the same units. Km, everybody should know this. I assume everybody here knows this. Km is defined back here on this. I'll put 3 lines for define. Is defined as ES over ES. So you can see it has units of molar. Molar over molar is molar. Okay, so this has units of concentration. It doesn't have to be molar. It could be millimolar, as long as everything's millimolar or nanomolar or micromolar or whatever. It just needs to be units. And of course they have the same units. And so when S0 is small, then V0 is equal to Vmax times S0 over Km. And remember that Vmax, from going back here, is equal to K2 times E0. So this is also equal to K2 over Km times E0 times S0. So in other words, this part at low S should be a straight line whose slope, this is y equals mx, right? Whose slope is equal to K2 over Km times E0. And that's valuable. Times E0. But sometimes people will actually plot it as V0 over E. And then it's simply equal to K2 over Km. If I were to bring that over. And then as in the other limit, would be S0 is bigger than Km. And then under these, you can see what's going to happen to, when S is big, what will V equal to? V0 equal? Equal Vmax. Okay, just from up here, if S is big, then you can ignore this guy, and then because S0 is big, and then these guys cancel, and then it's just equal to Vmax, which makes sense because we know that we've gone as fast as we can go. So if we increase S even more, what's going to happen to the velocity? Nothing. It could go down eventually if it poisons the enzyme. We haven't drawn that yet, and that often does, but nothing because it's maxed out. All right, and so up here, it's going to be level, and that's going to be Vmax. Well, or K2 as I've drawn it here. It's equal to Vmax divided by E0, but that's equal to K2. So if we extrapolate that back. And then there's like some smooth stuff in between that connects the two. So that's kind of the limits. in our lab, we like to call these conditions k cat over km conditions. For obvious reasons. You get k2 over km, and k2 is equal to k cat under these very simple conditions. We'll come back to that. And then we like to call these, so again, remember this is equal to k2 times E naught, or that if we plot v0 over E naught, it's simply equal to k2, which is equal to k cat. And so we call these guys k cat conditions. All right.
I'm sorry.
Yeah.
What did you write about the conditions on the left?
It's k cat over km. So it gives you k2 over km, which you can see here. That it gives you k2 over km as a slope, and k2 is equal to k cat. So people call these k cat over km conditions, and then they call these other ones k cat conditions.
Cat for catalysis.
Yeah. Let's see. I feel like I've probably almost covered enough, and like it would be better just to talk, because if I just let me look at what I have here. I just have sort of a bunch of different ideas. Oh, I know one thing we should talk about. But let me ask if there's any questions, or you want me to go back and go through it one more time, or is everybody good? All right. Let's go. Let's talk about one more thing. It's kind of going back at the same time. So if I hit back and go back to Km, Km is right here, and it doesn't work. I want some way to highlight things, like draw a box or something. Oh. Okay, so if we go back to this here, you guys all know what KDs are, right? And so one question that often comes up is whether or not Km is equal to KD. You want to talk about that? It's a really important concept. Okay, so so KD is really ignoring. It's just binding. It ignores. KD ignores this stuff here. So let me copy this. Oh, look at that. I'm getting the hang of it. All right. Or not. There we go. Okay, let's go talk about KD. Oops. I like my white pen. My chalk. All right, KD versus KM. Ready? If you ever have Marty Bollinger on your committee, you better be able to answer this question, or me maybe, or David, or any of us. So so Km we just showed was equal to K minus 1. Hold on. Let me make this a little smaller. I know how to do this now. Okay. Yeah, that's better. So Km is equal to K2 plus K minus 1 over K1, right? We just showed that. And KD, well, if I paste, or let me just go back and write what we had before, it's just as fast. We had ES, a complex with ES, the Michaelis complex goes to E plus P. But this is this is not what really happens with KDs. With KDs, there's no chemistry, and so what we want to do then is to block out these steps. Now this guy is still equal to K1, and this is still equal to K minus 1. So then we just have simple binding, and we'll write it down in, we can write it out as the rate law if you want, or we can just write it down as KD. Let's write out the rate law. So so the forward rate, good practice, is equal to K1 times E times S, and the reverse rate is equal to K minus 1 times ES. And what's true at equilibrium? What's the relationship between rate forward and rate reverse? Why am I flickering? I don't understand. I'll have to ask her about that. They're equal to each other because the two rates are equal, right? And so when you set them equal to one another, then you end up with K1 times E times S equals K minus 1 times ES. Or that ES over ES is equal to K minus 1 over K1, which we know is equal to the KD. Okay, so the KD is K minus 1 over K1. And it has what units? Molar, right? Because it's KD. So small means tight or weak with KDs? Tight. Okay? So this is the opposite of what they teach you in chemistry, not the opposite, the inverse. Oh, let's go back to this for a second, because speaking of which, I forgot to justify why we use Km. So graphically on here, right, Km is, so I plotted them out that way. What I should also do is plot them out the other way. With Vmax. Let's go back and just plot it as Vmax. Sorry, not Vmax. My bad, V naught. So forgiving. Alright, and so this is the fastest it can go. That's called an asymptote. This is Vmax. So if you go back and you look at the equation up here, when S is equal to Km, what's the velocity equal to? S can equal Km. It's 1/2. So when S is Km, you end up with Km over 2Km, which is 1/2. So at 1/2 Vmax, that's your Km. Okay, so you should be able to really quickly look at data and just guess your Km just by looking at it. And it's the concentration where usually people analyze it this way. So they find Vmax over 2, go over, hit the curve, come down, and that concentration of S is approximately the Km. I mean, we actually fit it, but it's good to be able to do that. And that's one of the reasons for using Kms versus Kas, or using KDs. And remember here it's a Km, not a KD. So let's talk about KDs. have measured KDs, and so we said that KDs are equal to K minus 1 over K1. Not sure. So let's move this down here, and we'll say that this guy is equal to K minus 1 over K1. So we probably could even derive a relationship between Km and Kd if we wanted to, by going up and substituting into here, right? So we could say that this is equal to K2 over K1. Plus Kd. So when you look at Km and you ask, is Km equal to Kd, the answer is, well, it depends. I don't know if this is coming from this. I don't think it is, because it was doing it. Just check other connections. I think it has to do with how these things are talking to each other. So are they? Yeah, I can't reproduce it. So are they equal to one another? Well, it depends, right? So it depends on the relationship of K2 to K1. I'll see if I can figure that out between now and next time. What's causing it? It's getting worse for some reason. So the answer is it depends, and it depends on K2 versus K1. No, that's not right. I guess. Well, I've written it down that way, but it really depends on the relationship between K2 and K minus 1. Why isn't that coming out in the math? Because if you look up here, maybe you guys can help me, I'm a little stuck. So if K2 and K minus 1, you can see that if K2 is big or small compared to K minus 1, that will affect whether or not you lose this term here. And so, but I've written it out that way. But I'm not sure that this is really all that useful. I'm going to get rid of that. So it really depends on K2 versus K minus 1. And you can see that up here in that equation. And so so again, if we take limits, and those limits can be, and then we'll stop here. K2 is big compared to K minus 1. Or K2 can be small compared to K minus 1. And if K2 is big, then Km is approximately equal to K2 over K1. But here, Km is approximately equal to K minus 1 over K1, which is equal to Kd. And here this is not equal to Kd. And you can try to figure out if it's bigger or smaller than Kd, right? And that's where the equation that I erased might help. So Km is equal to K2 over K1 plus Kd. And if K2 is bigger, then Km therefore must be greater than Kd. So the Km is bigger than the Kd in this instance, because K2 is bigger than K1 up here. But here they're equal to one another. And so you need to worry about this. So if you do steady state kinetics and K2 is bigger than K1, then the 1/2 V max point will overestimate your Kd. The binding will be tighter than what you see it is by pulling it off the graph. But in this case, they will equal each other. And I've got all sorts of different ways to show you guys how to think about that by doing things like graphing reaction profiles, free energy versus reaction profiles. And I'll do that next time. Anybody have any questions? Is this helpful? Is it pretty familiar for most of you? Is it stuff you've seen before, or like good refresher?
Yeah, good refresher.
I have some pretty advanced stuff, but we'll start with this. That we can pull in later. I mean, all sorts of things. I've got a long list of topics that I can do. I think once a week will be enough after doing this. I'm much further than I thought I would get in sitting down for one time. And I think it would be too much to process, and we're all too busy to do it twice a week over the summertime. So let's just stick with once a week. We'll stick with this time, and I'll let you know if I need to shift it. We'll stick with noon during the week. We'll try for Wednesdays, but stuff comes up. I might be on a thesis committee. I might be traveling. Things like that, or something else might come up and I might have to shift it. But I'll try to give you a little bit more notice than 2 hours next time. But yeah, I've got all sorts of really cool things that I can show you guys later. In particular, single turnover kinetics are really important in modern day enzymology. In fact, that's what most people do. Steady state kinetics are done, but generally only to fit all your data inside of it. Most stuff is done with single turnover, where the enzyme is present in substrate concentrations and the substrate is present in limiting concentrations. And that's possible with recombinant DNA and protein overexpression, RNA overexpression. And there's a lot of similarities, but there's a lot of differences. And then also in this set of notes, I have things where we can look at more complex mechanisms, like, for example, what happens when you get more realistic on this part here, and instead of just having ES magically turn into E plus P, you let it go to EP, and then you let E plus P dissociate, and things like that, and also more on plotting data. And so when you do that, it's really powerful, because then you can start to write down any mechanism, and you can do kinetic shortcuts. But ultimately, what you want to be able to do is two things. I mean, this is just review. You want to be able to do two things, in my opinion. You want to be able to read a paper, and you want to be able to derive the kinetics that are in there, just to feel satisfied and understand it, and also to see if it's right or not. And then you want to be able to capture their data, replot it, and refit it yourself. But then even more important and even harder is you want to think about your own system and what it's doing, and get insight from kinetics and structure and whatever it is. Be able to write something down like this, but it won't look like that, because your system will always be more complicated than that. And then derive the rate equations in a reliable and general way. Like, I always call it like deriving equations from scratch. And I'll show you guys some tricks for doing that, but I won't be able to show you every possible scenario. But if you have some examples, like in your research that you're thinking about, or something you've read, like, if there are cases actually where substrate can poison the reaction. So and I can try to, no promises, but I can try to deal with that. I mean, you could imagine that one substrate binds, but then there's a second substrate that binds in addition that's weaker, and it binds to a second site, on E, like this, say. We'll put it on the left side, like that, the second site. And that's got its own KD or KS for substrate binding. But this one doesn't go to give you products. It just poisons the reaction and it binds weaker. How do you handle that? It's not there. It might not be in here either. It might not even be in there. And it might be somewhere in the literature, but you can't find it. And can you derive that? Can you come up with something? And how do you do it? And when you're done, does it make sense? And are you satisfied with it? Those are what you really need to do. That's what graduate school is really about. And so we can try to get to that point. And if you come in with examples, because otherwise I'll just be doing general examples or examples out of my group. I'm just going to erase all that. Undo. I think that would be good. Okay. Class is dismissed.